Hi everyone, welcome to our physics class. In the previous classes, we have studied about purely resistive circuit, purely inductive circuit, purely capacitive circuit. What is the meaning of resistive circuit? AC voltage is applied to circuit containing only resistor is called purely resistive circuit. So, what is the expression for instantaneous current flowing through purely resistive circuit? That is I is equal to I naught sine omega t. So what is the phase difference between current and voltage in purely resistive circuit? That is zero. Current and voltage are in phase. So what is the value of power factor? Cos phi. Cos phi is equal to cos 0. That is equal to 1. Power factor in purely resistive circuit is equal to 1. So what is the average power over one complete cycle in purely resistive circuit? That is the product of RMS value of voltage and RMS value of current. And power loss is maximum in purely resistive circuit. That is the product of RMS value of voltage and RMS value of current. So the next one is inductive circuit. What is that? What is the meaning of inductive circuit? AC voltage is applied to circuit containing only inductor. That is called purely inductive circuit. The instantaneous current flowing through the inductor is I is equal to I naught sine of omega t minus pi by 2. That means the current lags behind the voltage by an angle pi by 2 radian, or voltage leads the current by an angle pi by 2 radian. What is the phase difference between current and voltage in purely inductive circuit? That is pi by 2 radian. Phase difference between current and voltage in purely inductive circuit is pi by 2 radian. So what is the value of power factor? Power factor is cos pi by 2. Cos pi by 2 is equal to 0. The power factor in purely inductive circuit is equal to 0. Power loss is also equal to 0. Average power over one complete cycle in purely inductive circuit, that is also equal to 0. And what is the meaning of capacitive circuit? AC voltage is applied to circuit containing only capacitor is called a purely capacitive circuit. The instantaneous current flowing through the capacitor at any instant of time, the instantaneous current flowing through the capacitive circuit, that is I is equal to I naught sine of omega t plus pi by 2. That means the current leads the voltage by an angle pi by 2 radian, or voltage lags behind the current by an angle pi by 2 radian. So what is the phase difference between current and voltage in purely capacitive circuit? That is pi by 2 radian. So that is the phase difference. So what is the value of power factor? Power factor is cos phi. Cos phi is equal to cos pi by 2. So that is equal to 0. So power factor in purely capacitive circuit, that is equal to 0. So average power over one complete cycle in purely capacitive circuit is equal to 0. Power loss is also equal to 0. Okay, power factor in purely resistive circuit 1, power factor in purely inductive circuit is 0, power factor in purely capacitive circuit is equal to 0. So these are the topics we have already studied in previous classes. That is very important. Okay, so this is alternating current part 5. Okay, well, let's start today's class. So in this class, we are going to discuss about the next very important, most expected 5-mark derivation in this chapter. That is LCR series circuit. AC voltage is applied to circuit containing inductance, capacitance, resistance when they are connected in series. Okay. So this is derivation of expression for impedance, and current in LCR series circuit by phasor diagram method. So this is a very important 5-mark derivation. Okay, so first here let us consider inductor, capacitor, resistor. All are connected in series. Means the inductor, capacitor, resistor are connected end to end. AC voltage, that is V is equal to V naught sine omega t, that is applied. AC voltage V is equal to V naught sine omega t, that is applied to a circuit containing inductor, capacitor, resistor. Those are connected in series. Okay. So this is series LCR circuit. So what is the meaning of inductor? So inductor is a circuit element which offers certain opposition to the flow of varying current. Inductor is a circuit element which offers certain opposition to the flow of varying current. That means increasing current or decreasing current or growth current or decay current or any change in current. That is the meaning of inductor. What is the meaning of inductor? Inductor is a circuit element which offers certain opposition to the flow of varying current. Varying current. What is the meaning of capacitor? Capacitor is a device used for storing electric charge. So what is the meaning of resistor? Resistor is a circuit element which offers certain opposition to the flow of current. Okay. Actually here, inductor, capacitor, resistor, all are connected in series. So the current flowing through inductor, current flowing through inductor, okay. So current flowing through capacitor and current flowing through resistor. That is in the same direction because all are connected in series. Okay, so current flowing through inductor, current flowing through capacitor, current flowing through resistor is same. Okay, the rotational vector of current in purely inductive circuit, purely capacitive, purely resistive, that is same. Okay, so here current flowing through inductor, current flowing through capacitor, current flowing through resistor, that is in the same direction. Okay, but the voltage potential difference across L, that is VL, actually that is leads the current, is it not? The potential difference across L is VL, so which leads the current by an angle pi by 2 radian. So in purely inductive circuit, so what amount of current flowing through the inductor? I is equal to I naught sine of omega t minus pi by 2. That means current lags behind the voltage or voltage leads the current. Is it not? Current flowing through the purely inductive circuit. That is I is equal to I naught sine of omega t minus pi by 2. That is current lags. Current lags behind the voltage or voltage leads. Okay, this is the potential difference across L. Okay, so VL which leads the current by an angle. How much? By an angle pi by 2 radian. Okay, right? So the potential difference across C, that is VC. So which lags behind the current, by an angle pi by 2 radian. The potential difference across C, that is VC, so which lags behind the current by an angle pi by 2 radian. So in purely capacitive circuit, the current flowing through the capacitor is I is equal to I naught sine of omega t plus I is equal to I naught sine of omega t plus pi by 2. That means the current direction of current. So in purely capacitive circuit, the instantaneous current flowing through the capacitor is I is equal to I naught sine of omega t plus pi by 2. That means the current leads the voltage, or voltage lags behind the current. So here voltage, that is lags behind the current by an angle pi by 2 radian. So this is in purely capacitive circuit. Okay, in purely inductive, what happens? The current lags behind the voltage, voltage leads the current. In purely capacitive, current leads the voltage, voltage lags behind. Voltage lags behind the current by an angle pi by 2 radian. So the potential difference across or, that is VR. The potential difference across or, that is VR. So that is in phase. That is in phase. Okay. So the potential difference across or is that VR, that is in phase with current. Right? What is the phase difference between current and voltage in purely resistive circuit? That is zero. Current and voltage are in phase. That means both are moving in the same direction. The rotational vector of current, the rotational vector of voltage, both are in the same direction. Okay, so this is the phasor diagram of purely inductive. This is the phasor diagram of purely capacitive. This is the phasor diagram of purely resistive. Now we have to combine all these three phasor diagrams. That is the phasor diagram of LCR series circuit, and that is very, very important. Now look at this phasor diagram. Actually, this is a phasor diagram of LCR series circuit. Okay. So the potential difference across or, that is VR, that is in phase with current. Okay. So actually, so this green arrow mark shows the rotational vector of current through inductor, through capacitor, through resistor. Okay, so here current flowing through inductor, current flowing through capacitor, current flowing through resistor, that is same. So this is the rotational vector of current. Okay, this is I. Okay, so the potential difference across R, that is VR. Potential difference across R is VR. It is in phase. Okay, it is in phase with current. There is no phase difference between the current and voltage, right? The potential difference across R is VR. It is in phase with current. That means VR, rotational vector of VR and current, that is in the same direction. Okay, and that is represented by the vector OA. The potential difference across R is VR. It is in phase with current. Okay, and is represented by the vector OA. So here OA vector represents the potential difference across R. Okay, that is in phase with current. So there is no phase difference. There is no phase difference between voltage and current, right? So the potential difference across L, that is real, which leads the current by an angle pi by 2 radian. Is it not? So this is O. So that is represented by the rotational vector OB. So vector OB vector represents the potential difference across L, that is VL, which leads the current. It leads the current by an angle. How much? By an angle pi by 2 radian. Okay, the potential difference across L is VL, which leads the current by an angle pi by 2 radian. Okay, so the potential difference across the capacitor is VC, which lags behind the current by an angle pi by 2 radian. So that is represented by the vector OC. Okay, so vector OC represents what? The potential difference across capacitor is that VC lags behind the current. VC lags behind the current by an angle pi by 2 radian. So actually here our assumption. So this is very important point. So our assumption. So our assumption is VL assumption is VL is more than VC. So this is actually our assumption. VL is more than VC. For example, VL is equal to 5 volt. So VC that is equal to 3. So VL is 5 volt, that is vertically upward direction. VC is 3 volt, that is vertically downward direction. So both are here rotational vectors. So VL is vertically upwards. So VC is vertically downwards. So both are acting at the same point. So what is the resultant? Two vectors acting at the same point but in opposite direction. So what is the resultant? Resultant is P minus Q. Is it not? Q vector acting at the same point but in opposite direction. The magnitude of P vector is much greater as compared to the magnitude of Q vector. The resultant is P minus Q. So here the resultant is VL minus VC. Resultant of VL and VC is VL minus VC. The resultant of VL and VC is VL minus VC, and that is represented by the vector OD. The OD vector represents the resultant of VL and VC. So that is along which direction? Along the direction of the greater magnitude vector. So here the greater magnitude vector is VL. So that is why the resultant of VL and VC, that is along the direction of the greater magnitude vector, that is along OB. Okay, right? So VL minus VC, what is this? The resultant of VL and VC, so that is along vertically upward direction. Okay, so after that we have to calculate the resultant of VR and VL minus VC. Okay, so VR that is along OA, VL minus VC that is along OD. Two actors acting at the same point which are mutually perpendicular to each other. So the resultant actually lies along the diagonal of the rectangle. Here we have to apply the parallelogram law of vector addition. Is it not? If two vectors acting at the same point, so the resultant lies along the diagonal. So let us consider this one as vector OE. So vector OE represents the resultant of VL minus VC and VR. So that is V. So V is the resultant voltage. What is the meaning of V? V is the resultant voltage across inductor, capacitor, and resistor. All are connected in series. So I is the resultant current, V is the resultant voltage. Now you can consider phi is the phase difference. Phi is the phase difference between the resultant current and the resultant voltage. Okay, so phi is the phase difference between the resultant current and the resultant voltage. So this is the phasor diagram of LCR series circuit, and this diagram, so and arrow marks are very important. Okay, so now let us start the derivation. So in the triangle that is OAE. So in the triangle OAE, actually we have to apply the Pythagoras theorem. So OD magnitude is VL minus VC. So AE magnitude, that is also same, is it not? OD magnitude, AE magnitude, both are same. AE is also VL minus VC. So in the triangle OAE, OE square, OE square, that is equal to OE square is equal to OA square plus AE square. OE square is equal to OA square plus AE square. So OE square is V square, right? OA square, that is VR square, and AE square, AE square is VL minus VC whole square. But what is the value of VR? VR is I into R. What is the value of VL? According to Ohm's law, I into XL. XL means the effective opposition offered by inductor to the flow of AC, right? And VC is I into XC. XC is the effective opposition offered by capacitor to the flow of AC. So this is according to Ohm's law. So R is the effective opposition offered by resistor to the flow of AC. XL is the effective opposition offered by inductor to the flow of AC. XC is the effective opposition offered by capacitor to the flow of AC. So resistance, inductive reactance, capacitive reactance, all are measured in terms of ohm. Ohm is the SI unit of resistance, inductive reactance, and capacitive reactance. So V square is equal to, so VR square is IR whole square, that is I square R square plus VL is I into XL minus VC is I into XC whole square. So V square is equal to I square R square plus. So here I is taken as common and take it as outside the square bracket. what happens? That is I square. First I is taken as common. After that, I is take it as outside the square bracket. So it will become I square. I square of XL minus XC whole square. So V square V square is equal to I square or square. Uh, Actually, here I square that is taken as common. I square is taken as common. I square of or square plus XL minus XC XL minus XC whole square. Right? So V square divided by I square that is equal to R square plus XL minus XC whole square. So V divided by I that is equal to square root of R square plus R square plus XL minus XC whole square. But according to Ohm's law, V by I that is equal to Z. Actually here Z is called impedance. What is this? This is called impedance. Impedance means the effective opposition offered by inductance, capacitance, resistance when they are connected in series to the flow of AC. So impedance that is also measured in terms of ohm. What is the meaning of impedance? The effective opposition offered by inductance, capacitance, resistance when they are connected in series to the flow of AC. That is called impedance. Impedance is also measured in terms of ohm. So ohm is the SI unit of impedance. So now comparing these two equations, we will get the mathematical expression for impedance. So call this as equation number 1, call this equation number 2. Now from equations 1 and 2, we can conclude that Z is equal to square root of square root of R square plus XL minus XC whole square. Or in other words, Z is equal to square root of R square plus XL is L omega, XC is 1 divided by C omega whole square. This is another mathematical expression that is equal to root R square plus L omega minus 1 divided by C omega, because XL is equal to L omega, XC mathematical expression is 1 divided by C omega. Okay, what is the meaning of impedance? Impedance means the effective opposition offered by inductance, capacitance, resistance when they are connected in series to the flow of AC. So that is the meaning of impedance. Okay, so the instantaneous current flowing through the LCR series circuit, that is I is equal to V by Z. What is the value of Z? Z is the root of square plus Xn minus Xc. So if VL is more than, actually this is our assumption, if VL is more than VC, then the impedance is square root of R square plus XL minus Xc whole square. Suppose VC is more than VL, impedance is not equal to root R square plus XL minus XC, that is XC minus XL whole square. Okay, so what is this? The instantaneous current flowing through LCR series circuit. I is equal to V divided by second. So the instantaneous current flowing through the LCR series circuit in terms of phase difference, that is I is equal to I naught sine of omega t minus phi. Actually, here the current lags behind the voltage by an angle phi radian. So this is the instantaneous current flowing through LCR series circuit. If the inductive reactance is more than the capacitive reactance, or the potential difference across L, that is more than the potential difference across capacitor. So in that case, the current lags behind the voltage. So now actually the LCR series circuit, that is behaves like purely inductive. Okay, if VL is more than VC, the LCR series circuit behaves like purely inductive circuit. Okay, so this is very important for 5 marks. Okay, so the next one is derivation of the same derivation of expression for impedance and current in LCR series circuit by phasor diagram method. But here our assumption is not same. That is, VC is more than VL. Previous derivation, our assumption is VL is more than VC. But here in this derivation, our assumption is VC is more than VL. Okay. So again, let us consider inductor, capacitor, resistor. So all are connected in series. AC voltage, that is V is equal to V naught sine omega t, that is applied to circuit containing inductor, capacitor, resistor. All are connected in series. So the current flowing through inductor, current flowing through the inductor, current flowing through the capacitor, current flowing through the resistor, that is C, right? This is the rotational vector of current through inductor. This is the rotational vector of current through capacitor. This is the rotational vector of current through resistor. So the potential difference across L is VL, which leads the current by an angle pi by 2 radian. This is not the potential difference across L is VL, which leads the current by an angle pi by 2 radian. The potential difference across C is VC, which lags, behind the current by an angle pi by 2 radian. The potential difference across C is VC, so which lags behind the current by an angle pi by 2 radian. The potential difference across R is VL, which leads the current by an angle pi by 2 radian. The potential difference across C is VC, which lags behind the current by an angle pi by 2 radian. The potential difference across R, that is VR, that is in phase with current. Okay, the potential difference across R is VR, that is in phase with current. So there is no phase difference between current and voltage in purely resistive circuit. Now combining all these phasor diagrams. Now look at this phasor diagram carefully. So here rotational vector of current through inductor, capacitor, resistor, that is same. This is the rotational vector of current through inductor, capacitor, resistor. Actually, this is a resultant current flowing through the inductor, capacitor, and resistor. So the potential difference across R, that is VR. Okay, so that is in phase with current. This point is very, very important. Okay, the potential difference across R, that is VR. VR is in phase with current, so there is no phase difference between the current and VR. What is the phase difference between VR and I? That is zero. That means both are moving in the same direction. So the potential difference across R is VR, that is in phase with current, and is represented by the vector OA. OA vector represents the potential difference across R, VR, that is in phase with current. And the potential difference across L is VL, which leads the current by an angle pi by 2 radius, and is represented by the vector OB. Okay, OP vector represents the potential difference across L, VL, which leads the current by an angle pi by 2 radian. What current lags behind the voltage by an angle pi by 2 radian. Okay, so and then the potential difference across C, that is VC, which lags behind the current by an angle pi by 2 radian. So the potential difference across C is VC, so which lags behind the current by an angle pi by 2 radian. So and is represented by the vector OC. So here our assumption is VC is more than VL. That means here VC is equal to 5 volt, for example. VC is equal to 5 volt, and VL, that is equal to 3 volt. So VC acts vertically downwards, so VL acts vertically upwards. So what is the resultant? If two vectors acting at the same point, which are in opposite direction, so what is the resultant? Resultant is here not VL minus VC, because here VC magnitude is greater. It is 5 volt. Okay, the resultant is VC minus VL, and that is along the direction of greater magnitude vector. So here greater magnitude vector is VC. Is it not? So here resultant acts vertically downwards. The previous derivation, that is vertically upwards, because our assumption is VL is more than VC. Okay, so VL acts vertically upwards. So VL magnitude is more than VC. So that is the resultant of VL and VC is VL minus VC acts vertically upwards. But here VC magnitude is more than VL. VC magnitude is more than VL. The resultant of VC and VL is VC minus VL. The resultant of VC and VL, that is VC minus VL, so which acts vertically downwards. Okay, so this is VC minus VL, so which acts vertically downwards, right? The direction of resultant, that is along the direction of greater magnitude vector. Here the greater magnitude vector is VC, so that is why resultant acts vertically downwards, right? So now VC minus VL and VL acting at the same point, which are mutually perpendicular to each other. Here we have to apply the parallelogram law of vector addition. The resultant lies along the diagonal. So this is the resultant voltage. It is cancelled. This is V. V is the resultant voltage, and is represented by the vector OE. Okay, I is the resultant current flowing through LCR series circuit, and V is the resultant voltage across the LCR series circuit. So the phi is the angle made by the resultant voltage and the resultant current. Okay, so now let us start the derivation. So in the triangle OEA, so actually we have to apply the Pythagoras theorem, right? So the triangle OAE, so OE squared OE squared is equal to um, OA squared plus AE squared, right? So OE squared is V squared. V squared is equal to, so V squared is equal to V squared is equal to OA squared, that is VR squared plus AE. So actually the resultant of VC and VL, that is VC minus VL, and is represented by the vector, that is OD. Vector OD represents the resultant of VC and VL. Okay. So OD is VC minus VL. So even A is also same, that is VC minus VL. The magnitude of OD is equal to the magnitude of A. So A square is VC minus VL whole square. VC minus VL whole square. So, but the value of VR according to Ohm's law, this is IR, and VC, that is I into XC, right? And VL is I into XL. So V squared is equal to VR squared, that is I squared or squared plus VC is I into XC minus VL, that is I into XL whole square. So V squared is equal to I squared or squared plus I take as common, take it as outside the square bracket. What happens? It will become I squared of XC minus XL whole square. So V squared is equal to I squared, that is just take it as common, I square of R square plus XC minus XL whole square. Okay, so V squared divided by I square, that is equal to V square divided by I square is equal to R square plus XC minus XL whole square. Okay, so V divided by I, that is equal to square root. Square root of R square plus XC minus XL whole square. So V divided by I, which is according to Ohm's law. V divided by I, that is equal to Z. Call this as equation number 1 and call this as equation number 2. Now, from equations 1 and 2, we can conclude that Z is equal to square root of R square plus XC minus XL whole square, or Z is equal to square root or square plus X is L omega. Xc is 1 divided by C omega. 1 divided by C omega. Xl is L omega, right? So this is the mathematical expression for the impedance. So the current is I is equal to V by Z. So I is equal to V by Z. Z is square root of R square plus XC minus XL whole square. And this is the current flowing LCR series circuit. So the instantaneous current through, in this case, the instantaneous current flowing through LCR series circuit I is equal to I naught sine of omega t plus phi. So actually here the current leads the voltage. Current leads the voltage by an angle phi radian. Okay. So I is equal to I naught sine of omega t plus phi if xc is more than xl. If xl is more than xc, then the instantaneous current is I is equal to I naught sine of omega t minus phi. Current lags behind the voltage by angle phi radian. So if xc is more than xl, then the instantaneous current flowing to LCR series circuit is I is equal to I naught sine of omega t plus phi. So here current leads the voltage by an angle phi radian. Okay, so this is alternate method. Okay, now let us discuss about the impedance triangle of LCR series circuit. Actually, this is impedance triangle. This is angle phi. So the perpendicular in impedance triangle for LCR series circuit. Suppose if XL is more than XC, XL is more than XC. The perpendicular value is XL minus XC. And the base is the resistance. Hypotenuse is Z. Okay, what is the value of Z? If XL is more than XC, that is square root of R square plus XL minus XC whole square. XL minus XC whole square. XL minus XC whole square. Right? So this is actually the impedance triangle of LCR series circuit if XL is more than XC. Suppose if XC is more than XL, the perpendicular is XC minus XL. So the expression for the impedance is that is equal to root R square plus XC minus XL whole square. Okay. So here the first very important point, expression for phase difference. Expression for phase difference between current and voltage in an LCR series circuit in terms of XL and XC. So in this triangle, what is the value of tan phi? So tan phi is perpendicular. Tan phi is perpendicular divided by base. So perpendicular is XL minus XC. So base is R. So phi is equal to tan inverse of XL minus XC divided by R. So this is actually the phase difference between the current and voltage. Okay, the phase difference between current and voltage in an LCR series circuit in terms of XL and XC. So in terms of R and Z, what is the phase difference? So again in the triangle, what is the value of cos phi? Actually, this is the power factor in LCR series circuit. Okay, the quantity cos phi is called the power factor, right? Cos phi that is equal to R divided by Z. Cos phi is equal to R divided by Z, right? Cos theta is base divided by hypotenuse. Cos phi is equal to R by Z. So phi is equal equal to cos inverse of R by Z. So this is the mathematical expression for phase difference between current and voltage in an LCR series circuit in terms of R and Z. Okay. So after that, let us discuss about some very important special cases. If XL is more than XC, if XL is more than XC, then tan phi is positive, phi is positive. So in this case, the voltage, the voltage leads, is it not? Voltage leads the current by angle phi. Okay, or the current lags behind the voltage by angle phi. So, in this case, LCR series circuit purely behaves like inductive circuit. So, this point is very, very important. So, if XL is more than XC, then tan phi is positive, phi is positive. That means the voltage leads the current by angle phi radian. So therefore, the LCR series circuit is purely behaves like inductive circuit. Purely behaves like inductive circuit. If XC is more than XL, then tan phi is negative. Tan phi is negative. Phi is also negative. Is it not? X is more than XL, so tan phi is negative. So even phi is negative. So in this case, the voltage lags behind the current by an angle phi radian. So in this case, the LCR series circuit is purely behaves like the capacitive circuit. LCR series circuit behaves like purely capacitive circuit. Okay, so in this case, LCR series circuit behaves like inductive circuit. So in this case, LCR series circuit behaves like capacitive circuit. So if XL is equal to XC, then what is the value of tan phi? Tan phi is 0. What is the value of phi? So phi is also equal to 0. So actually here the current and voltage and current are in phase. That means there is no phase difference between current and voltage. Now the LCR series circuit is behaves like a resistive circuit. Just behaves like a resistive circuit. If XL is more than XC, LCR series circuit behaves like inductive circuit. XC is more than XL. Okay, so LCR series circuit behaves like capacitive circuit. If XL is equal to XC, LCR series circuit behaves like resistive circuit. So these points are very, very important. Actually, this is the condition for resonance. So when inductive reactance is equal to capacitive reactance, LCR series circuit is said to be in resonance. Okay, when inductive reactance is equal to capacitive reactance, LCR series circuit is said to be in resonance. Okay, so for LR circuit, for LR circuit, that means only inductor and resistor are connected in series. So what is the value of impedance? Impedance is Z is equal to square root of R square plus XL square. Here Xc is equal to 0. So the impedance triangle of LR circuit. So the perpendicular is only XL, base is R, hypotenuse is Z is equal to root R square plus XL square. So that is the impedance triangle for LR circuit, and this is the mathematical expression for impedance. Okay, so squaring on both sides, what happens? Z square is equal to R square plus XL square. XL square is equal to Z square minus R square. So XL is equal to square root of Z square minus R square. So XL is L omega. So omega is 2 pi f is equal to root Z square minus R square. So L is equal to root Z square minus R square divided by 2 pi f. So this is the mathematical expression for inductance, that is in LR circuit. What is this? Mathematical expression for inductance in terms of impedance and resistance. That is equal to root Z square minus R square divided by 2 pi f. Okay, for CR circuit, so the mathematical expression for impedance is Z is equal to root R square plus XC square. Okay, so Z square is equal to R square plus XC square. So XC square is equal to Z square minus R square. So XC is equal to square root of Z square minus R square. So Xc is 1 divided by C omega, that is equal to root Z square minus R square, right? So C is equal to 1 divided by omega, that is 2 pi f into root Z square minus R square. So this is the mathematical expression for capacitance. Okay, in case of CR circuit. So this is the mathematical expression for inductance. So that is in LR circuit. L is equal to root Z square minus R square divided by 2 pi r. So this is the mathematical expression for capacitance in PR circuit. That is C is equal to 1 divided by 2 pi f into root Z square minus R square. So this is the mathematical expression for phase difference between current and voltage in LCR series circuit in terms of R and Z. And this is the mathematical expression for phase difference between the current and voltage in LCR series circuit in terms of XL and X. Okay, these points are very, very important. Okay, thank you.